Welcome back, everybody, to INE's CCIE Data Center Nexus switching class. In this section, we're going to continue our discussion of virtual port channels. We're also going to talk about some more of the specifics about the different failure situations in vPC, and then what are the negative impacts of that, and then some of the ways that we can solve this from a design point of view. Now, as we talked about up to this point, in vPC, there's going to be two devices that are the vPC peers. One is the primary, one is the secondary. The goal of the feature is that we're taking a physical triangle topology and we're changing it into a logical point-to-point topology. Now, the potential problem we then have is that since the upstream switches, either the Nexus 5Ks or the Nexus 7Ks, have their own individual control planes, the problem we could run into is that we could have this active-active or split brain type of situation where the control plane is broken between the vPC primary and the vPC secondary, and it results in the secondary assuming the primary role and the primary maintaining its own primary role. So the way that we normally would prevent this is with the peer keep alive and the peer link, where again the peer keep alive is going to have the UDP unicast packets going back and forth. It's just a basic ping between the neighbors. And then we have the peer link that is actually used to synchronize the control plane protocols. So things like the MAC address table, the ARP cache, the other consistency parameters that are exchanged with the Cisco Fabric Services over Ethernet protocol, that's what's going to be running over the peer link. Now, under normal cases, when there is a failure of the peer link, the vPC secondary device is going to suspend its local member ports of the vPC and any of the SVIs that are the VLAN instances of the vPC member ports. So the idea behind this is that the secondary doesn't necessarily know if the primary has gone away. It just knows that the control plane communication between them is broke. So it's going to shut down its local ports and then allow the vPC primary in order to continue to forward the traffic. Now, under most cases, this is what we would want to prevent the split brain or the active-active, where both of the devices become the vPC primary, and then we have a problem in the layer 2 forwarding. But there are some potential negative impacts of this, especially when we have orphan ports in the vPC topology. And now, as we talked about before, what the orphan port means is that it is a layer 2 link that is connected to the vPC peers that is single connected either to the vPC primary or to the vPC secondary. Now, the issue that we run into is that the orphan ports don't follow the same forwarding for the data plane as the other normal member ports do. Whereas we talked about that peer check for traffic that is being forwarded over the peer link, normally when we do flooding, like if we have a MAC address broadcast, it's going to go out the member ports and it's going to go out the peer link. When the remote device receives it in the peer link, it's not going to go out other member ports, but it can go out the orphan ports, which are, again, the single attached devices. So we run into a potential problem then that if there is a failure and there are orphan ports, if the secondary vPC peer is the default gateway for the orphan ports, so the layer 3 interface, that layer 3 interface is going to be suspended, and then the orphan ports are going to be isolated from the rest of the network. So really the only way to prevent this is simply not to use orphan ports in the first place. That we do not want any port that has only single connectivity to the vPC peers while that port is using the same VLAN as any of the vPC member ports. So if we have a completely separate VLAN that is just for the orphan ports, that's going to be fine because those VLANs would not normally be forwarding across the peer link to begin with. Now, in most designs, you typically would not want to have orphans at all on the vPC peers. You would use separate switches, maybe like your Catalyst 6500, for single attached hosts. Then anything that is going to be dual attached, those are going to go to the Nexus that is running the vPC feature. Now, again, the only real way that we can prevent this is just to not to have the orphan ports to begin with. So vPC peers, ideally, they're only going to have dual attached neighbors as they go downstream. We'll also see that there are some potential problems in the failure detection of the vPC domain. Now, the normal case is that if the vPC peer link goes down, the secondary is going to wait for a certain type of timer to expire. So there's a hold timer or hold timeout, and there's a keep alive timeout that have to expire. Once this expires and it has not received a keep alive from the VPC primary, it is then going to assume the VPC primary role and continue to forward. However, after the timer has expired and we do receive a keep alive, this is the case where the secondary will disable its member ports and then not continue to forward downstream towards those members. So in this case, essentially the VPC secondary becomes disabled. It's essentially just removed from the VPC domain. The next issue we potentially could run into is that once the failure occurs and the secondary disables its VPC member ports, if the primary device then completely fails, the secondary member ports that are suspended are not going to come back into the up state. And the reason why is that the secondary is not continually checking the VPC primary to see if it is still available once we have this initial failure situation. So in this kind of corner case scenario, both the VPC primary and the VPC secondary could be effectively disabled, and we would not be able to actually forward traffic through the topology. So let's go ahead and take a look at this on the command line. If we look quickly back at the topology that we're currently using, we have the Nexus 7Ks at the top. Excuse me, the Nexus 7Ks at the top. That have the VPC down towards the 5Ks. And then likewise on the 5Ks, we have the VPC that is going up towards the 7Ks. So in this case, we're going to be specifically looking at this on the 5,000 switches, and we're going to see what happens when we disable the peer link that is between the devices. So let's go back to the command line. And the first thing that we want to know is who is the VPC primary role and who is the VPC secondary role. So if we look at the show VPC, we see that we have the peer keep alive is up, which is good. We have the adjacency over the peer link, which again is going to be with that Cisco Fabric Services over Ethernet protocol. And then we have our actual member ports, which in this case are port channel 7. This is the link that is going upstream towards the 7Ks. Now the specific peer link, we can see that this is VLAN 50. We could also see that 5K1, this is the primary VPC device. We look at the 5K2 and look at the show VPC. This is the secondary device. This is normally what we would want to see, that one is the primary, one is the secondary. That split brain or that dual active, what we're trying to prevent is that both of them become the primary device at the same time. Next, let's go to the port channel 50 here that's being used as the peer link between the devices, and we're going to shut this link down. Now, before we do this, let's turn on logging to the console, so let's say terminal monitor, and let's look at the debug VPC, and in this case, let's debug the peer link on both sides. Debug VPC peer link. Next, on the primary device, I'm going to go to the port channel that is the VPC peer link, and we're going to disable this. So this is essentially simulating a link cut between the primary and the secondary. So the secondary is going to detect this. It's going to say that the bundle is down, which is the peer link in this case. It says the local role is slave. We're listening for the out-of-band timers. This basically means for the peer keep alive link now, we're waiting to see, once these timers expire, is the primary still active? If we look at the show VPC now, it says that the peer link is down, but the keep alive status is up. So this means that there was just a failure either locally of the peer link, there could have been a failure remotely of the peer link, but the devices do still have basic layer 3 reachability to each other. So we are able with those UDP echoes to send the packets and receive the packets because I've not shut down the management 0 interfaces that are used for that out-of-band keep alive. But if we look back here at 5K2, we see that the member ports of the VPC, which in this case is port channel 7, it says that since the peer link is down, the member ports now need to be disabled. So if we look at this from the scope of the physical topology, it effectively means that we won't be able to forward any traffic up in this direction. Because the member ports in this case are talking about Ethernet 1/8 to 9 and Ethernet 1/10 to 11. This would then be one of the reasons why you would want to make sure that the fabric extenders are actually dual attached. Because the way the topology is set up now is not exactly what we see here. There's no redundant connections from the parent switches to the downstream fabric extenders. So these links are not there. They are only single attached. And now, since there has been a failure of just the peer link that is between the VPC devices, the VPC secondary says I have to disable the port channel that is going upstream towards the 7Ks. It essentially means that these devices are now going to be isolated from the network. So if we were to take a look at the routers in the topology, where router 2 is connected to 5K2 and router 3 is connected to 5K1 through the fabric extenders, we should see that we're no longer going to be able to have reachability between these devices simply based on the peer link failure in the topology. So ideally what we would have is not this case of essentially having orphan ports. So the orphans now include any of the devices that are attached to 2K2, which is server 3 is dual attached, and we have router 2. Now, even though we do have multiple links that are going from the fabric extenders up to the parent switch, these links are not dual homed. They're doubly single homed to the same switch, which means that there was a failure of the peer link, but the keep alive was still okay. We were able to do the ping over the out-of-band management between them. The secondary says, I have to prevent this dual active scenario. The result of that is I'm going to shut down my member ports, and furthermore, my orphans are now disabled from sending any traffic into the VPC. So in this particular case, we don't actually fall back to spanning tree. If we look at on 5K2 and look at the show interface status, the links that are going downstream, which are effectively these VLAN 20 ports, the VLAN 20 ports downstream are fine, but the upstream facing interfaces, which are E1/8 to 11, if we see E1, 8 to 9, and then 10 to 11, actually these ones I had manually shut down before. Let's bring those back up. 1/10 to 11. Interface E1, 10 to 11, no shutdown. Then let's look at the show interface status. We see that these are disabled because the VPC peer link is down. So even though there's nothing physically wrong with these ports, we cannot use them now for forwarding and any of the members that were previously part of the virtual port channel. Now, to solve this, what we would simply do is take the fabric extenders and dual home them to the parent switches. So if we did not have the orphan ports, if we had a connectivity up to 5K2 and connectivity up to 5K1, then this path would be disabled when the peer link connectivity is lost between them, but we're still going to have reachability through that portion of the topology. So this is going to be one of the biggest design considerations of the VPC. You need to make sure to avoid this situation where you have orphan ports, or essentially single attached ports, to the individual VPC peer. Now, for the next failure scenario that I was mentioning, where essentially we have a failure of the primary, but the keep alive is still there. So let's say there's a failure of the VPC peer link between the neighbors, but the keep alive is fine. The secondary is going to figure that out, and then it's going to disable its own local ports. If I now were to go to 5K1, and let's save our config here, let's say copy run start, and we were to reload, so we're basically simulating like a power failure in the network. When we look at the VPC on the secondary switch, it says now the keep alive has failed. If we show VPC, says the peer link is down, but now also the peer keep alive is down. So the peer is not reachable through the keep alive link. But notice what has happened with the state of the member ports. They're still what? They're still down here. So in this kind of corner case situation where the peer link first fails and the secondary device says the primary is still alive because the peer keep alive is there, I have to disable my local vPC peer ports, or my local vPC member ports, I should say. Then there's a complete failure of the primary device. In this particular case, the vPC secondary is not continually checking to see if the vPC primary is available. Now, one way that we can prevent this is a feature that is available on both the 5K and the 7K, but is off by default, which is known as vPC auto recovery. Now, auto recovery is going to allow the secondary to assume the primary's role in certain very specific failure situations. So in the case that we had now, the vPC peer link went down. This is what is triggering the initial failure situation to happen, and we're trying to reconverge from this. The first thing the secondary is going to do once the peer link goes down is going to wait for these hold timers and the keep alive timeouts to expire. So these are configurable values. If we look at the show vPC peers, peer keep alive, we can see what's the keep alive timeout, what's the keep alive hold timeout. So we wait for the first one to expire, the 5 seconds. Then we're going to wait an additional 3 seconds after that. Once this 8-second timer has expired, if the primary still has a keep alive, then we will disable our own local ports. That was the first step that we saw. But again, the problem is we're not constantly checking for this after our ports are disabled. So the secondary is waiting for the hold timers to expire. We still receive a keep alive because the peer keep alive link is still up, so the secondary is going to suspend its local member ports. Then we have the case that the primary completely fails. So there's some configuration problem, we can't figure out what's going on, or there's some operational problem, so someone decides just to reboot the box. So now the primary is completely failed, but the secondary doesn't re-enable its member ports. And this is the first failure scenario that auto recovery is trying to solve. In this case, with auto recovery on, the vPC secondary will be actively checking to see if the primary has gone away after the peer link is down. So again, the first thing that is triggering this whole situation is that the peer link communication was lost, but the keep alive was still there. As long as the keep alive is still there, the secondary is not going to enable its vPC member ports. It's going to keep those in the down state. But in this corner case where the vPC secondary is continuing to check for the keep alive, and the keep alive is then not received from the primary. So the primary completely fails. The vPC secondary can promote itself to the primary and unsuspend the vPC member ports. Now, when the primary eventually comes back, we're not automatically going to preempt the roles, which means that the primary becomes the operational secondary, and the secondary becomes the operational primary, just so we don't have to go through another convergence event in order to continue to forward the traffic. Now, there's also a second situation that auto recovery is going to help us with here, is that if there is a power outage in the data center, so we have the two vPC peers, either the 7Ks or the 5Ks, both of them, either they reboot or the power goes out and then they're coming back up. Now, once the initial boot up occurs, if the vPC peer link does not come up, we cannot do the initial election to figure out who is the primary device and who is the secondary device. So it means that the virtual port channels are never brought up in the first place. So in this case, nothing is working in the data plane because the peer link went down. Someone's trying to fix the problem. They reboot both of the boxes. Both of them come back. The peer link doesn't come back. The vPC is going to be disabled on both the primary and the secondary because there was never an election to begin with. Now, with auto recovery, there's an exception to this that says a single vPC peer can elect itself to the primary even if the peer link was never established. And this is the feature that has replaced what used to be called reload restore. So reload restore in the newer versions is not available in this syntax. It's going to be preempted by this feature here, auto recovery. But there are some potential problems that auto recovery could actually introduce into the network. So there are certain cases that if the VPC pairs fail in a certain order, it actually will cause the split brain, which is what we're trying to prevent. So ideally, you would provision enough redundancy in the topology that that's not a feasible case. Like you would have the redundant supervisors, you would have redundant line cards, you would have redundant power in the chassis, so that it's possible maybe one of them goes down, but it wouldn't be reasonable statistically for both of them to be failing at the same time. So you should ideally be able to have at least one of them forwarding. But in this particular case, let's assume that auto recovery is on. So auto recovery is not on by default, but let's assume that we had configured it. Then there is somehow a link cut of both the peer link and the peer keep alive between the neighbors. So the links both go down, but both of the chassis are actually functional. Now the VPC primary is not going to do anything when this happens. The VPC primary is just going to continue to stay primary. However, the VPC secondary, in this case, eventually will elect itself as the primary. Once we have the hold timer and the keep alive timer expire, then once we have the auto recovery timer expires, the secondary is going to promote itself to the primary, and it is going to re-enable its VPC member ports. In this particular case, both of them are going to be primary, and since there are two separate control planes, this is what we call our dual active or our split brain. It's essentially a catastrophic failure of the network, because we're not going to be able to forward traffic properly in the data plane. Half of the traffic is going one way, half of the traffic is going the other way, and ultimately the applications usually are not going to be able to deal with that. So realistically, in this type of scenario, there's not much that you can do in order to fix this. If you had a network down emergency, really the only thing that you can do is to just power off the secondary. Or you could go into global configuration and simply say no feature VPC, which is automatically going to destroy all of the configuration, which is going to allow you to fall back just to your regular spanning tree forwarding. The other solution to this, as I mentioned, is just to make sure that you're provisioning enough physical redundancy in the network. That you would have dual supervisors, you have multiple line cards, you have redundant power, that it would be very, very rare that you could run into this case where both of them are going to fail at the same time, and then you would run into the active-active, the split brain situation. So if we now look at the result of this, once the 5K1 should come back here. On 5K2, when we look at the show VPC, the peer is now alive. So the routed link between them, the management 0, came back and we're able to do the UDP pings. But the peer link is still down because that's shut down on the remote side. This means that the secondary device cannot automatically promote itself to the primary device. So the VPC member ports are still going to be disabled. So let's go here now to the VPC config. Let's say show run VPC. We're going to go to our VPC domain 5 and say that we have auto recovery on. It says auto recovery is going to allow you to wait for 240 seconds by default to determine if the peer is unreachable. So now let's assume that everything is fine in the network. If we look at the show interface port channel 50, this is the peer link that we have administratively down. So let's say that this link is back up. This is fine. The VPC secondary should detect this. It says we're going through the compatibility check. And eventually we should see that the member ports are going to come back up once we have this normal delay for the initial convergence. If we show VPC, the consistency check was successful, but we're still waiting for this timer to expire. So we can see eventually reconvergence happens, and the secondary says the primary is up, everything is fine, so now I'm going to put my member ports into the up state. Now normal forwarding is going to be restored. So if we go to router 2, if we ping router 3's address, we should see that we have basic reachability. So let's go ahead and keep sending these packets so we can see what happens when the failure occurs. Again, we now have the problem where the peer link fails. So the primary shuts down the peer link. Secondary says there's a failure of the peer link. I now need to start looking at that out-of-band keep alive. Which is here. So we're now suspending our ports. So we had the 3-second timers. Again, if we look at the show VPC peers, or show VPC peer keep alive, we had the timeout and the hold timer of 5 and 3 seconds respectively. So it took us 8 seconds total after the failure occurred to basically demote our member ports. So now they're in the suspended state. If we show VPC, we see the local ports are down because the peer link is down. Auto recovery is enabled though. If we show run VPC, we see that in global config, auto recovery is on. If we show VPC, the peer is still alive, so the keep alive is okay. Let's now say completely that 5K1 goes down. So I'm going to connect actually to the console of this here. Which is N5K1. And I'm going to disable the management link. We know the management link here is what we're using for the peer keep alive, for the VPC. So eventually the secondary is going to figure this out, says the keep alive now also failed. If we show VPC, the local member ports are still disabled, and also notice that our switch virtual interfaces, we're now shutting them down. Now in this case, the 5K doesn't actually have any SVIs, we're not doing any layer 3 routing, but if we were to look at this on the 7K, we would have the same effect. That when the secondary disables its VPC member ports, it also disables its layer 3 SVIs that have VLANs that match up with the VPC members. So for example, if we have VLAN 10 that is forwarding over the VPC member ports, and we also have interface VLAN 10, it means that if I'm the secondary and the peer link fails, not only do I disable the VPC member ports, but I also shut down the SVI. So eventually we'll see, once the timer expires, and we should see a log message here, let's show VPC. We're now the operational primary. And I believe in this case I was debugging, let's show debug. I was debugging VPC peer keep alive. If we just said debug VPC, that's going to show us everything. Debug VPC all or debug VPC errors. The problem is a lot of these debugs are very chatty, and it's fairly difficult to sort through them to see exactly what you're looking for. But in any case, we can see that now, only since auto recovery was on. If auto recovery was off, which is the default behavior, the secondary would have not promoted itself back to the primary state here. If we now go to router 2, we would assume that the forwarding is going to work, but it actually does not, because now we have that split brain type situation. Where if we go to 5K1 and look at the show VPC, from the console, show VPC, this guy says it's the primary. Its local VPCs are up. If we go to the secondary and likewise show VPC, it says I'm operationally the primary, so now both of them are active, or that split brain type behavior. So even though the links are up, we don't have layer 3 connectivity. And again, the reason why is that we basically have a mismatch of the way that the traffic is being load balanced, that some is going in one direction, some is going in another direction, and it's not properly forwarding in the data plane. So really we have a couple different ways that we could fix this. We could just go to the secondary and say no feature VPC. That's going to completely destroy it, and we should not have the split brain there. Or ideally what would be the case is just that the links come back up. So if the management interface is back, and we then look at the show vPC, once the peer keep alive status comes back, and this is really why this link is so important in the network, we need to make sure that we have enough physical redundancy provision. Like in the case of 7K, you would want to do this on multiple line cards, so that if one line card goes down, it doesn't necessarily cause the keep alive to go down. But in this case with the 5K, we were doing it just over the management ports. We can see now the peer is alive. And if we go back to the first 5K and show vPC, we see that there's not a preemption here. So even though that the keep alive is back up, which is the peer is alive, this secondary vPC peer is operational primary, and the primary peer is still primary. So let's bring the peer link back up. Once the peer link is up, this is the one that's actually allowing them to do the election of who is primary, who is secondary, because that happens over Cisco Fabric Services. It does not happen over the UDP keep alive. The keep alive is just a ping between them. Now the secondary realizes that it should not be the operational primary. And this is going to take a little bit to converge here. This first switch now became the operational secondary. So eventually it should work itself out where one of them is going to say either I was the primary and I'm staying the primary, or I was the secondary and now I became operational primary, but only one of them can be maintaining that role at a time. And we can see on 5K1, it's now shutting down its member links of the vPC. And to fix this, we're going to have to go to the port channel, basically disable them manually, and then try to bring them back up. Because with auto recovery off, the secondary is not automatically going to re-enable its member ports. So you can use the auto recovery feature. The problem is you can run into those strange situations where you basically cannot recover from the failure without either rebooting one of the devices, without manually shutting the link down, the peer link down and bringing it back up, or if you were to just say no feature vPC, that's going to remove all of your configuration of the vPC and then fall back to just your normal spanning tree forwarding. Okay, so let's see, we have a couple questions here. There is no preempt in vPC, correct. That's what the issue is here. They were both primary at the same time. There's a question, what is the priority keyword used in the vPC domain? That would be if you wanted to change what the election is. So if we look at this on the command line, if we show vPC, now the member ports are back up. Okay, everything is in the normal situation now. We see router 2 and router 3, they have connectivity to each other. Additionally, there is a priority value. If we show vPC, peer keep alive, and let's show vPC role. So the local role priority is 32,667. If I were to go to 5K2, and let's go under vPC domain 5, the system priority, and I want to say that a lower numerical value is a higher priority. Let's check this out here, though. If we now show vPC role, my priority is 1. Let's now shut down the peer link on both sides and bring it back. Show vPC role. says the port channel is being suspended because there's a VPC domain or system ID mismatch. Let's take a look at the command reference here. There is a way to change this where you can change what the role is, but normally it doesn't really matter which is which. It's just that there is a primary and there is a secondary. But just for your own administration point of view, you may want the one particular box to be the primary all the time. So let's look at this from the main navigation path. So starting from the main documentation page, we're going to go down to switches, to data center switches, Nexus 5000 in this case. Then instead of configuration guides, we're going to go to reference guides and the command reference. Then I believe this is going to be under let's check the master index, actually. That's going to tell us exactly where this is. And the command I'm looking for here is under the VPC domain, system priority. Let's search for system dash priority. This is under VPC. It says to manually configure system priority for the virtual port channel, use the system priority command. The default priority is 32.667. This is the link aggregation priority, which is not what I want. I want the VPC role priority. Let's go back to the configuration guide, which VPC I want to say is going to be under interfaces, then configuring virtual port channels, and let's search for priority. Manually configuring the VPC peer switch role. It's the role priority, not the system priority here. So let's say no system priority. 1. The role priority, let's change that to 1. Okay, it says the VPCs will be flapped on the current primary switch while attempting the role change. Change will take effect after the user has reinitiated the VPC peer link. So I basically need to go to the peer link, shut this down, bring it back up. Then if we show VPC role, it says my local role priority is 1. And on 5K1, if we show VPC role, now we are the secondary. So you can change this like you can see here with the, again, the command was the, let's show run VPC. The command was the role priority. But really, at the end of the day, it doesn't matter which is the primary, which is the secondary. As long as both of them are not primary at the same time, that's the problem that we're trying to avoid, that we have that dual active or the split brain behavior, which means that we're going to have a failure of the forwarding in the actual data plane. There's a question, if then both the peer link and the peer keep alive are cut, this priority option will help or not. It's not really going to help at all. The only thing it's changing is just who is elected the primary, but it doesn't prevent the problem of you possibly having the split brain to begin with. So really the only option is that if auto recovery was on and split brain still happened, the only way you can really fix it is just by disabling one of the peers, which means that you're going to fall back to just 50% of the forwarding. Okay, there's a couple other questions. If the peer link fails and the keep alive is up, the secondary disables the member ports, but wouldn't the primary do that too since the peer link is down? That's the difference here, that the primary does not disable its VPC member ports. Only the secondary is required to disable its VPC member ports. So the idea from a topology point of view, let's assume that we have the 5Ks that are directly attached to the end hosts. So we have our server down here, and we have two 10 gig links. So 10 gig 1 10 gig 2. We then have the VPC peer link between them, and we have the VPC peer keep alive. Then we're going upstream to the rest of the L2, L3 network. Okay, so that's upstream towards the core. We have the link cut, or there's some sort of communication problem on the peer link. The device on the left is the primary. Device on the right is the secondary. The secondary says the peer link went down, but the keep alive is still okay. So this means that I have to temporarily disable my VPC member ports. The result of this should ideally be that we're not cutting off connectivity to the end host. It's just that its only way to forward traffic is now going to be in that direction. So now, as opposed to having a 20 gig port channel, we're just reduced to having the one 10 gig single link. But the problem that we're trying to prevent to begin with is that if the peer link goes down and the keep alive goes down, then the secondary promotes itself to the primary. So now we have the split brain. This one is active, and this one is active. When the traffic forwards out, it's eventually going to get dropped. And that's what we saw with router 2, even though the links were still fine. When both of them were running in the primary state, we weren't actually able to exchange any packets in the data plane. So it's kind of an odd situation, and really the way to prevent it that they're doing automatically is just saying, I'm going to cut off half of the connectivity until you fix the problem, which is that the peer link went down. You need to address whatever the layer 1 or layer 2 problem is between the devices. Okay, there's a question. If a pair of 7Ks with a peer link between them, and they each have a 2K FEX connected, and a server has an LACP ether channel connected to each 2K. So let me start to draw this out actually. Okay, so we have two 7Ks. 7K1, 7K2. And they each have effects. Now the 7K with effects, this supports just single homing. Okay, it supports static pinning. It doesn't support VPC, at least in the current versions that we're working with. So we have the static pinning that's going down to the 2Ks. We also have the peer link between them. Then we have the peer keep alive. We then have an end server that is dual homed to the FEXs. When the peer link fails, will the 2K on the secondary 7K shut its ports down to the server, or will it at least stop sending LACP to the server so that the link can be taken out of the server's port channel, or will the server black hole the traffic into the 2K because it thinks the port is still up, especially if it is a non-LACP port channel? So the question then becomes, the question is, if the peer link goes down, what actually happens to this port on the secondary? Does it physically get disabled, or does it just stop sending LACP? And we can actually test this here real quick. If we look back, let's take a look at our physical topology here, where we have the second 5K is going down to the second FEX here. Okay, the second FEX is then going down to this server 3. Okay, there's dual attachments here. And we're going to run LACP on those ports, so we're forming a port channel between the two of them. So what we want to look at is if the peer link goes down, so if we shut that port channel 50 down between the two 5Ks, from the server's point of view, does the NIC card get disconnected, basically is the question. Or is it up to the server to try to figure out through some other control plane mechanism whether the link has failed? So let's check this out. Let's go to server 1 here, or actually not server 1, that would be server 3. And let's just go to the network card properties. These ports here are going to N2K to port 6 and 7. We can see both of them are enabled. Okay, both of them are enabled right now. And then the team 0, this is the LACP link. This is where we're running the port channeling between them. Okay, let's go back to the Nexus, 5Ks. And on 5K2, let's look at the show VPC. It says I'm the primary. So I'm now going to change my VPC priority. Let's go to VPC domain 5. The role priority, let's say it's the highest, 65535. Then I'm going to shut the peer link down and bring the peer link back up. What this should do is to force 5K1 to be promoted to the primary. So let's show VPC. It says I'm the primary. Show VPC on 5K2. This is the secondary. If we show interface, the peer link is up, but the member interfaces are down. So let's do this. Let's shut down the link again, the peer link, and then bring it back up. Shutdown, no shutdown. Then on 5K2, let's look at the show VPC. So the VPC, the member port is still down. What I may need to do is manually flap this, shut it down, and then bring it back up. Show VPC, ports are still down. Okay, we should be currently just converging here. Eventually port channel 7 should come up. Okay, port channel 7 is up. So now what we need to do is basically take the, let's see, how would we need to do this in this design? What we would have to do is, because our network right now looks like this. We have 7K1, 7K2. So they have a VPC going down to the 5Ks, 5K1 and 5K2. So this is our back-to-back VPC here. Then down towards the FEXs, so this is in 2K2 and N2K1, what I would need to do is to put this into a VPC first. So let's say that this is VPC 102 for FEX Associate 102. It's basically going to be an orphan VPC. So if we show, let's look at the running config. The links that go down to the FEX here are ports 6 and 7. So let's say on interface E1, 6 to 7, this is channel group 102 mode active, or actually mode on, down to the FEX. Interface port channel 102 is switch port mode FEX. So you can see changing those downlinks that are going down to the fabric extender, it has to take it offline and then it has to come back online. So it takes a little bit for this to converge here. So the port channel is now switch port mode FEX and FEX Associate 102 and VPC 102. Let's look at the show VPC. says this has failed because the peer does not have the corresponding VPC. I actually am not going to be able to show this in this topology because I would have to configure it as dual active. But what would happen though, the final result is going to be that the server just forwards that direction. Now, whether it does this by actually disabling the link, like an administratively shut down, or whether it does it by not sending LACP, they should have the same effect. Because if the server is running LACP, it's going to know that there's a problem with the channel and that this link should be removed from the team, basically. Because if this is the secondary, then the VPC from its perspective is going to be, the VPC is going to have to be disabled. Let me double check on this. I'll check on this after class, and then when I go through the next video series going through some more of these specific examples, then I'll make sure to put this one together so we can see what the exact functionality of it is. Otherwise, it would take a little bit of time to try to rebuild the topology like that right now. Okay, there's another question. If you have two 5Ks VPC'd with a FEX single-homed, and the hosts are VPC with one link to each FEX, one FEX dies, are you simply left with orphan ports? Would traffic flow uninterrupted? Basically, a loss of a FEX does not cause any VPC reconfiguration. You should still be able to forward. So let me see, what is this topology then? You're saying if there's two 5Ks, so 5K1, 5K2, and you guys can start to see the type of failure situations you can run into with VPC. It gets a little bit hairy about all the different possibilities, the different results you can have. So if you have two 5Ks with a single FEX, a FEX single-homed, so that's actually what we have in this case. Okay, so 2K2 single-homed. One FEX dies. The hosts are VPC, one link to each FEX. That's actually the same situation we were just talking about there, which is in this direction. What's going to happen is that so let's say we have another member out here, another fabric extender that's part of a different FEX, so 2K3. If this fabric extender goes down, this now counts as an orphan. That's okay though, because now to reach it, you can go over the peer link and down. So in that failure situation where what used to be a VPC member port, if it becomes an orphan, that's when you use the peer link as kind of your last-ditch effort that's used in the data plane. So normally the peer link is going to be used just in the control plane, but in certain of these failure situations, it can be used in the data plane. What happens if just the VPC peer keep alive link fails? Okay, that's a good question. Let's actually take a look at that here. So right now, if we let me remove the other port channel, no interface port channel 102, and show run interface E1 6 to 7. So the FEX is there. If we show FEX, the FEX is online sequence. So you can see every time you make a change to those downlinks, it has to reinitialize. But in this case, actually, that didn't take that long. So if we show VPC, VPC is up. We go to router 2, we look at these pings, everything is still fine, there's still connectivity. So let's now say that just the peer keep alive goes down. So the management 0 is shut down. If we look at 5K2 and say show VPC, says the peer is not reachable through the peer keep alive. As long as the adjacency is still there, though, the VPC is fine. Now, the reason that this happens is that the peer keep alive link is basically a backup for the peer link. As long as the peer link is still up, that's really what's used to synchronize the control plane. and to make sure that we don't run into this dual active situation. So the failure scenario really only makes a big difference if the peer link goes down first, then you lose the keep alive afterwards, because the keep alive is what's preventing us from having that split brain situation. So obviously it is something that you would need to address. If the keep alive goes down, you don't want that to happen, but it's not automatically going to disable the member ports. Okay, we have a question, is the ideal design to maximize the physical redundancy and enable auto recovery, or should auto recovery be avoided? It should be fine to enable it. Just the thing is, you have to know what are the potential issues that you can run into. So the worst possible case scenario is going to be the split brain, which means that the data plane is just completely going to fall apart. So if auto recovery was not able to prevent that, then you have to have a last-ditch effort plan built in that all you have to do is just go to one of them, say no feature VPC, then it's going to fall back to just having one of them as a primary, and then you'll be able to forward the traffic. But the idea is that you should be able to engineer enough redundancy into the 7Ks that you would normally not run into this case in the first place. Because we have redundant control plane with the supervisors, we have redundant power, then we have redundant data plane with the different line cards as well. Okay, exactly. So we would need to maximize the physical redundancy by saying, let's have multiple M1 cards that we're going to use for the peer keep alive, multiple F1 cards that we're going to use for the peer link. So then if there's a failure of the power, chassis is still going to stay up because we have redundant grids. If there's a failure of one of the supervisors, we have the stateful switchover immediately, which is stateful, so we don't have to rebuild the control plane for the VPC. If one of the line cards goes down, it means that the VPC peer link is going to stay up and the VPC peer keep alive is going to stay up. You'd have to have like a very, very improbable, massive catastrophic failure really for the to run into this situation with the split brain when you're talking about the case of the 7Ks. There's a question here, if I bounce the peer link while the keep alive is down, will the peer link come back? Let's try that out. Let's go to port channel 50, shut it down. We should see that now, since I'm the secondary, if we show VPC, we should see that we have to suspend our ports. Actually, now I'm operational primary. Show VPC on the other side. This may have actually caused a split brain. It did. Now they're both running as primary. So if the keep alive fails and then the peer link fails, that's also kind of a non-recoverable situation. But let's now bring the peer link back up. Interface port channel 50, no shut. And show VPC. It says the peer keep alive is not operational. The peer was never alive. The peer link is down. It looks like it's not going to come back. But notice that the VPCs are not operational here. Let's look at the other side as well. Show VPC. On the secondary, it doesn't even show port channel 10. If we show port channel 7, if we show port channel summary, it says that this is up, but it's not part of the VPC. So it's basically just being treated now as a normal static port channel. So now let's re-enable the keep alive. No shut. This should force them to fall back in line, that once the peer keep alive comes up, and again, as I was talking about the order of operations before, that's why it's important that you actually do configure it in that order. You need to keep alive active first before you configure the peer link, otherwise the peer link is not going to come up, and you end up in this kind of recursive logic where the VPC just stays down. So once both of them are functional again, now the peer is alive, now we can form the adjacency, and then eventually now we can see port channel 7 is now back in the VPC. Now, within the scope of the CCIE lab exam, you could use the auto recovery feature. It's only one command to enable. This is more of an issue of a real-world design, of how do you actually need to provision the redundancy, and what's going to happen if you have certain failure situations, and then how can you deal with it. But like I said, worst case scenario, you would just say no feature VPC, and then you should be able to fall back just to normal spanning tree forwarding. There's a question, if both switches go down but only one comes back up, is auto recovery required for the VPC to recover? Yes, it is. So the situation is that both of the switches go down, so let's say you just power them off. You power one of them back on. Since the second one is down, the peer link never comes up. And if the peer link never comes up, then the VPC can never come up. So that's the second situation that auto recovery is trying to fix, that the switches reboot, peer link never comes up. Since we can't have the peer link, it means we don't elect ourselves the primary or the secondary, and the VPC has to be suspended. So in that case, if the peer link doesn't come up after a certain timer, I believe it's around 6 minutes or so by default, then you will elect yourself as the primary, even without the peer link being up, and then you can activate the local VPCs. There's another question. So in the case of a total chassis failure, the failure depends on what fails first, the peer keep alive or the peer link, correct? So it is subject to the order of operations, both from the configuration and then from the failure scenario. There's a question, when the peer link is down, wouldn't the switch transmit any other traffic? It can still be used for forwarding for non-VPC links. So if you have regular layer 2 Ethernet, or in the case you're doing fabric path, you still will be able to forward traffic over those links. Really, this is just within the scope of the VPC member ports, that we're trying to prevent the looping of their traffic. And since we have two separate control planes, kind of the best that we can do is just shut off half of the network, shut off half of the control plane, so we only have one box left. And the result is that we have just a point-to-point Ether channel, as opposed to having that triangle up to both of the VPC peers, and then the peer keep alive and the peer link on the back end for exchanging the control plane. Okay, there's one other case that I want to talk about with this before we get into our next topic, which is going to be multicast routing over the VPCs. And I mentioned this a little bit earlier. It's called the VPC peer switch feature. Now, with the default behavior of the VPC primary from the spanning tree point of view is the one that is going to be generating the BPDUs. So the spanning tree hellos basically to the downstream switches out the member ports. The primary VPC peer is the one that's in charge of doing that. Now, with the peer switch feature, it makes the VPC peers appear as if they're both the root bridge at the same time. So you would configure them both with the same priority. They're going to be sharing the same MAC address for the spanning tree bridge identifier, and they're both going to be sending essentially identical BPDUs downstream towards the member ports. Now, the reason that you would want to do this is that in certain failure situations where the primary goes down, and actually let me draw this out because it's kind of difficult to visualize why you would need this feature. So the case is that we have the primary VPC peer. We have the secondary VPC peer, and then we have the downstream device. Like this is our whatever switch downstream. Okay, we have the peer link, and we have the peer keep alive. This primary is also the root of the spanning tree. So let's assume that this is a layer 2 trunk. So it's a layer 2 trunk on both sides, and we have multiple VLANs. Maybe we have VLANs 10, 20, and 30. So this means that we're sending BPDUs for all three of these, 10, 20, and 30. The next thing that happens is that the primary fails. The secondary figures this out, and it eventually promotes itself to primary. Okay, so it says now I'm the operational primary. When it does this, since there is now a change in the root bridge, this guy becomes the root. The downstream switch has this link disabled because the primary is gone. But from their perspective previously, this was a port channel which was already our root port. Okay, this was already our root port from spanning tree's point of view. So technically, this is not a topology change in spanning tree then, because the downstream switch has had its root port that was the port channel. We still have the root port as the port channel. The only difference is that there's one less member of the link. So one of the physical members went away, but the logical port channel is still there, just with one member, and that is still now the root port. So up to this point, everything is fine. Okay, the next thing that happens is that the primary comes back. So now the primary is okay. The primary also is now going to start advertising itself as the root of spanning tree again, which means that the secondary switch, it doesn't necessarily have to change its role from operational primary back to secondary, because again, there's no preemption in the roles with the VPC peers, but where there is preemption is in spanning tree. So this guy no longer becomes the root, which means that we now need to do a rapid spanning tree protocol sync. So this port here now goes into the blocking state. We do the handshake of spanning tree, which is the sync. We figure out that the peer link is now the root port. Then once this is the root port, we can unblock the downstream link, do the three-way handshake, and then eventually move this into the forwarding state. The problem, though, is that this is going to take extra time to converge, because we have to disable from spanning tree's point of view, because remember, spanning tree is still running on top of the VPC. So from spanning tree's point of view, we put the link into blocking state, we do the handshake over the new root port, then we unblock the downstream interface, do the handshake again, and then we can continue to forward. So in certain high availability environments and low latency environments, you would not want this. Okay, the goal then is with the peer switch, the secondary VPC peer doesn't need to run the synchronization process again, because they're essentially both the same root bridge. They're sharing the same bridge identifier. And configuration-wise, this is only going to be one command. You just go under the VPC domain 5, and say peer switch. And actually, it looks like the 5K doesn't support it in this version. So let's look back at the 7Ks. Show run VPC. It's just this one command here, peer switch. So from their point of view, when we look at the show spanning tree, it says that I am the root. This is my bridge ID. If we look at 7K2, it should have the same thing configured, peer switch. If we show VPC, not show VPC, show spanning tree. If we look at these two fields, they're actually identical between the two of them. So it's kind of a strange case where this guy says it's the root, but notice it also has a root port. So it's a non-standard behavior for spanning tree. It's basically just a hack for the VPC process specifically that says the peers, I'm just going to make them appear as if they're the same root bridge. They're really not in reality. One of them will be the true root, and we can see this because one of the peer links was the root port. So 7K1 in this case is the actual root bridge, because on the root bridge, all of its interfaces are always in the designated state. But from anyone downstream of the root, we can see that some of these are designated, some of these are root ports. It means that even though it's acting as the root bridge, it's not actually the root bridge. So you'll see once we go to the VPC mode, we say VPC domain 7 here in this case, there's really not that many things that you can change syntax-wise. It's more of an issue of the overall design of the VPC, and that when you are initializing it, that you're doing it in the correct order, and that you're using a supported topology. Like that back-to-back VPC design we had to make sure that from the 7K's perspective down to the 5K, that all of those links were the same VPC members. Then likewise downstream on the 5K up to the 7K, all of those members had to be the same VPC. Otherwise, we can end up in an unsupported topology. And you will see as the versions progress, they continue to add new supported topologies. So what maybe doesn't work now, 6 months or a year from now, may be a new supported design that you can do with the VPCs. Okay, so we have a couple more questions here. Can you think of a situation where we wouldn't use peer switch? I'm not really 100% sure where it's going to cause a problem. So it may be one of those things that you would just want to enable when you run VPC. When we look at the show run VPC, you would probably want to run the peer switch feature. You would probably want to run peer gateway. You probably would want auto recovery on as well. Then let's see anything else here. There is another case that you may need to consider, and I'm not going to go through this because this would take quite some time to actually show this functionality. What you can also do under the VPC is to do enhanced object tracking, and there is a specific design guide. Let me search for this here. Nexus VPC enhanced object tracking. Create a tracked object. It says, beginning with release 4.2, if you must configure all VPC peer links and core-facing interfaces on a single M1 module, you should create a track object and a track list that is associated with the layer 3 link to the core and on all the links on the VPC peer link on both primary VPC peer devices. Once you configure this feature, and if the primary VPC peer device fails, the system automatically suspends all the VPC links on the primary VPC peer device. This action forces all the VPC traffic to the secondary peer until the system stabilizes. Okay, basically what this is saying is that if you have a certain design where you didn't employ enough redundancy, so you have a 7K that goes up to the layer 3 core, on the same physical line card, so this port here, the same physical line card that we're using for the peer link, it goes over to another chassis. The problem we can run into is that since this is all one line card, if the layer 3 core link is lost, we would also want to tell it to disable the peer link. And that's what the tracking example they're doing here is that where they're saying, and there is somewhere else they show the full configuration example of this, but it's similar to iOS where you create the tracked object, you then create a Boolean object to say if this and this and this occurs, so if my core link is down and my peer link is down, then I want to disable the VPC members. But the only case you need this in is that, again, you didn't provision enough redundancy physically to begin with. That if you had multiple M-series modules and you had multiple F-series modules, then if one of the line cards goes down, it doesn't necessarily mean that there's going to be a failure of the VPC domain. The only thing ideally it means is that you're just reducing your capacity a little bit. That one of the members gets kicked out of the peer link. That a few of the members get kicked out of the VPC member ports, but it doesn't mean that it's a full catastrophic failure of the full topology. Okay, there's a question. We follow a certain order while configuring VPC. What happens when we save and restore? The VPC members can come up first. So do you mean when you just do a normal reboot, like you save your config and reload? In that particular case, the VPC member ports just won't be initialized until the peer link and the peer keep alive is up. So the physical ports may be up, but you won't actually be able to forward any traffic on them until the convergence of the VPC peers happens. Okay, any other questions up to this point on the failure situations? Now, there's also a good presentation on Cisco Live about this, and let me take a look at that. Actually, let me bring up the specific link here. It's this one here. This was from the Cisco Live in London. It is 3146, Advanced VPC Operation and Troubleshooting. This talks about some of those scenarios that you can run into with the failures, and basically what is the workflow when the peer link goes down, when the peer keep alive link goes down. So I would definitely take a look at this. There is also the video on demand that's recorded of it. So if you go to that Cisco Live 365 site and then you search for vPC, you should see this as one of the presentations. So I definitely would take a look at this. Like I mentioned yesterday, you know, from the high-level overview, it seems like vPC is fairly straightforward, but once you start to really dig into the details, there's so many different possible topologies you can build. There's so many different failure situations that you would have to take into account, and then also to have a plan. If you do have a catastrophic failure, what do you do? And basically the end result is that you just have to disable one of the peers and then force the forwarding just to one of them. So you have basically a primary without having any secondaries. Okay, there's a question. If you're running OSPF or EIGRP on the SVI interfaces between the 7Ks, could you connect a separate layer 2 port channel for that purpose? Yes, you could. So it doesn't have to run over, actually, that's correct, you would want to do that. Okay, if you're routing between the 7Ks and you're routing for non-VPC segments, so basically for SVIs that are not part of your VPC members, then you would want to put that on a separate physical segment. You don't want that to go over the VPC pure link. You want it to go over its own layer 2 interface. There's another question. Does the proxy HSRP forwarding act the same on the 5Ks? To tell you the truth, I'm not 100% sure. I'm assuming that it would. Pretty much all the designs that I've seen with it are usually the 7K doing the layer 3 forwarding, but it should be the same type of logic because the VPC code is pretty much the same between the 5K and the 7K. You'd have to have the layer 3 card, the layer 3 daughter module, to actually see if the functionality is the same on the 5K, but I would assume that, that it is. Because it's not something really you need to configure, it's just a behavioral change that they made in VPC so that you can forward on behalf of the other active router. So HSRP actually becomes active-active, not active standby.